Usually, when we look at the engineering on these massive commercial vessels, there's this comforting expectation of just, absolute precision.
Right, you want things to be predictable.
Exactly. You get a low pressure alarm, you go check the physical line, you find a stuck valve, and you fix it. The troubleshooting is entirely binary.
We completely crave things that can be categorized, things we can physically touch, but step into the world of cryogenic fluid dynamics and that clean binary logic just completely falls apart.
It really does. You step onto a diagnostic landscape that is honestly intentionally deceptive.
Yeah, deceptive is the perfect word for it.
It's the absolute definition of mechanical phantom.
Yeah.
And if you are tuning in from OSG specifically, the crew and cargo engineers catching this via maritime satellite right out on the water, we have a highly targeted investigation for you today.
We really do. This one is right in your wheelhouse.
We are unpacking a phantom problem that is actively haunting the pipework of your DFTE vessels. And this issue, it masquerades as a standard mechanical failure.
Right, like a dropped gauge or a totally blocked flow meter.
Exactly, like the incidents logged recently on March 15th, 2026 and February 2026. But the reality is actually a terrifying scenario where you are unknowingly feeding your cryogenic low-duty compressors a steady diet of invisible freezing sludge.
Yeah, that sludge is the real culprit here, and we need to figure out exactly why this equipment keeps freezing up, specifically looking at why the differential pressure transmitters, their low pressure side, is completely choking out.
Right.
Our goal today is to validate the operational solutions proposed by your own cargo engineer, who, by the way, correctly identified that this isn't a mechanical failure at all.
Okay, let's unpack this. Because when most people think of liquid natural gas, they picture this uniform, pure substance.
Just a simple, happy methane molecule.
Right, just boiling away at minus 161 degrees Celsius.
Mm-hmm.
But looking at what the ship is actually ingesting and physically crossing over into the realm of fluid dynamics, the reality is entirely different.
Oh, completely. LNG is never a pure substance. It is a highly complex hydrocarbon cocktail.
A cocktail.
Yeah. Along with the pure methane, that cargo contains heavier non-methane components. We're talking C6 plus fractions, ethane, propane, butane, pentane, and even carbon dioxide.
Okay, so a whole mix of things.
Exactly. And the thermodynamics of this specific cocktail are the trap here. Pure methane stays a beautifully flowing liquid down at minus 161 degrees.
Right, which is what the system is designed for.
But those heavier molecules have vastly different temperature tolerances. Pentane, for example, freezes solid at roughly minus 130 degrees Celsius.
Wow.
And carbon dioxide freezes at minus 78 degrees.
So when the vessel's low-duty compressors are pulling vapor from the tanks to manage pressure or run the ship, that vapor stream isn't pure gas.
Not at all.
It's dragging these heavier, easily frozen molecules right along with it. And the hardware taking the hit first is the natural boil-off mist separator.
Which is such a critical piece of equipment. The mist separator is there to protect the high-speed rotating vanes of the LD compressor.
Because if they get hit by liquid...
if liquid droplets were to strike those spinning vanes at high RPM, the resulting pitting would cause catastrophic mechanical failure.
Right, total destruction.
Yeah. So the vapor stream first passes through a dense stainless steel knit mesh, and then immediately downstream of that, an incredibly fine 600 micron mesh strainer.
And 600 microns is what? Basically the width of a single grain of coarse sand.
Pretty much, yeah. Very fine.
So when the complex vapor stream hits that fine metal mesh, the pure methane gas is hovering at a temperature where it remains a flowing vapor. But those heavier hydrocarbons, the pentane, the C6 plus fractions, they've already physically crossed their freezing points.
Right, and they don't just liquefy. They crystallize and freeze solid directly onto the mesh.
It's like drinking what you think is pure water, only to find out it's loaded with invisible sugar that suddenly crystallizes and entirely clogs your straw.
I love that analogy. That's exactly what's happening. They are building a literal wall of ice inside the pipework.
And this brilliantly explains the diagnostic symptoms your fleet guidance warns about. The compressor is pulling just as hard, but the physical pathway is shrinking.
The volume drops.
Right. That drop in available volume is why the suction pressure gradually falls over time, even when the flow reading remains steady.
It also completely explains why the differential pressure transmitter goes haywire.
How so?
Well, the transmitter relies on these tiny sensing lines to read the pressure on both sides of an orifice. When those tiny sensing lines literally fill up with solid pentane ice, the instrument goes blind.
Oh, wow.
Yeah, it sends erratic, totally nonsensical data to the bridge because the physical mechanism measuring the flow is basically encased in a frozen hydrocarbon block.
I'm looking at this from the crew's perspective right now, and my immediate instinct is to ask, why don't they just reject the bad cargo at the terminal?
You'd think that would be the easy fix.
Right. I mean, the certificate of quality is an official legal document detailing exactly what is in those shore tanks. The crew should know exactly what chemical breakdown they're loading before they ever open the manifold.
You would hope so. But the fleet guidance explicitly warns that heavy hydrocarbon content may not be accurately reflected on the certificate of quality.
Wait, really?
Yeah. The sources actually document at least one nightmare scenario where a terminal produced a COQ confidently indicating 0 heavy hydrocarbon content.
0. Seriously. How does a major export terminal get an official, legally binding chemical breakdown entirely wrong?
It happens.
The shoreside gas chromatographs should be catching any heavy fractions before the LNG ever leaves the terminal pipework.
Well, shoreside gas chromatographs are sometimes calibrated to a narrow bandwidth. They intentionally ignore trace elements because they are just looking for the bulk product.
Okay, that seems like a massive oversight.
It gets worse. Furthermore, these heavy hydrocarbons stratify.
They separate out.
Yeah, they settle differently within the massive terminal shore tanks based on density. And terminal samples are often taken at the very beginning of the loading process.
Oh no. So because of that stratification, the heavy, dense sludge sitting at the bottom of the shore tank isn't pumped until the final hours.
Exactly.
The ship receives a massive, concentrated dose of sludge at the very end of the loading arm sequence, long after the official sample was taken and the perfect paperwork was printed.
Yep, it's a complete blind spot. The vessel ends up struggling with extreme contamination for the entire voyage. They're fighting a mechanical ghost because the official paperwork insists the problem doesn't even exist.
And that has to create immense friction for the engineering crew.
Oh, incredibly frustrating. They are looking at failing flow meters and dropping suction pressure, but the shoreside data tells them the fuel is pristine.
Okay, so the ship is inevitably loading these hidden heavy hydrocarbons, but they have to build up to the point of causing massive recurring blockages.
They do.
I was reading through the email from the OSG cargo engineer, and they pointed directly to the handling of the heel tank.
That is the key right there.
Managing the leftover liquid LNG kept in the cargo tanks to keep them cool for the ballast voyage seems to be the engine driving this chemical concentration.
And the physics of a ballast voyage confirm that cargo engineer's theory entirely?
How so?
Well, DFTE vessels are incredibly well insulated, right? But heat is still constantly leaking into the tanks from the ocean and the atmosphere.
We can never stop all the heat.
Exactly. That heat ingress drives a massive, slow-motion fractional distillation process. Heat preferentially boils off the pure light methane first because it has the lowest boiling point.
Leaving the heavier hydrocarbons behind in the liquid pool at the bottom of the tank.
Yes.
This is exactly like boiling a pot of salt water on the stove.
Oh, that's a good way to look at it.
Right. The pure water evaporates into steam, but the salt is too heavy to vaporize, turning the remaining liquid into a thick, increasingly concentrated brine.
That is precisely what happens. And if a vessel fails to rotate the heel tank and carries the heel in the exact same tank on consecutive voyages, they're continuously boiling off the light fractions and compounding the heavy fractions.
It just builds and builds.
Exactly. That leftover pool continuously transforms into a highly concentrated hydrocarbon sludge. Voyage after voyage, the purity of that heel just degrades.
So the unrotated heel tank explains the presence of this highly concentrated sludge. It acts as like the ammunition reservoir.
Right.
But the timing of the blockages means something operational is triggering the instant freeze right when the crew needs the compressors the most.
Yeah, the sludge is just sitting there until you pull the trigger.
Looking at the operational parameters, the pre-cooling process really stands out as the mechanism. Because to run the LD compressors safely at high speeds, the vapor must meet a strict minimum inlet temperature.
Usually minus 100 degrees Celsius, or in some specific operational conditions, a razor-thin margin of minus 90 degrees Celsius.
And on a ballast passage, the natural vapor simply isn't cold enough to meet that strict limit.
No, it's not. The system has to artificially drop the temperature.
Okay.
It does this by spraying atomized liquid LNG directly into the vapor flow, just upstream of the mist separator.
Wait, the vessel draws that liquid LNG straight from the heel tank.
Yep.
The exact same tank filled with that concentrated boiling sludge we just talked about. You are taking a liquid loaded with C6 plus fractions and forcing it through a spray nozzle.
What's fascinating here is the sheer physics of that exact moment. You're taking a pressurized liquid and forcing it into a lower pressure environment.
Okay, so the pressure drops rapidly.
Right, the sudden pressure drop from the spray nozzle causes an immediate temperature plunge. This is known as the Joule Thompson Effect.
The Joule Thompson Effect.
Exactly. The rapid expansion of the fluid absorbs heat, drastically dropping the temperature of the atomized spray in literally milliseconds.
Oh, here's where it gets incredibly ironic. Because of that Joule Thompson Effect, those heavy fractions instantly crystallize midair.
They do.
They literally turn into microscopic ice bullets that cement themselves directly to the 600 micron strainer. We are literally manufacturing ice directly onto our own protective filters just to keep the machines running.
It is the ultimate operational catch-22.
It really is.
I mean, during a loaded passage, the vapor is usually cold enough that you can avoid pre-cooling entirely. But on a ballast voyage without pre-cooling, the LD compressors will quickly trip on high temperature.
And if the compressors trip, the vessel loses its ability to manage the cargo vapor pressure.
Exactly.
So the crew is stuck between shutting down the plant or knowingly spraying freezing sludge into their own filters.
The fleet guidance basically insists on keeping the pre-cooling flow to an absolute minimum, just enough to barely maintain the suction temperature above the trip limit.
You're essentially just trying to delay the inevitable freezing for as long as possible.
Right, just buying time until you can properly deal with the blockage.
So once those 600 micron filters are entirely cemented in pentane ice, how do you get the ship breathing again without destroying the compressors?
Well, there are two ways. The Fleet Reference Guide outlines a temporary fix using an N2 purge and a massive permanent fix known as hot gassing.
Let's start with the temporary fix. You stop the LD compressors and purge the suction pipework with N2.
Right. Ambient N2 stored on the vessel is dramatically warmer than the cryogenic temperatures of the pipework.
Okay.
Flooding the system with nitrogen warms the internal piping past minus 30 degrees Celsius, and minus 30 degrees is the specific thermal threshold where those crystalline hydrocarbons finally melt back into a liquid state.
Oh, I'm connecting this directly to the 2022 handover notes regarding the slow-draining NBO drain pot.
Yes.
When those C6 plus fractions melt at minus 30 degrees, they do not revert to a thin, clear liquid like water. They manifest as a dark brown, highly viscous sludge.
Like cold, thick syrup.
Exactly. So when the engineering crew opens the drain valve on the NBO drain pot and it's barely dripping, it is not a mechanical failure of the valve itself.
Not at all.
They are trying to gravity drain thick syrup out of a pipe engineered for highly fluid liquids.
That's spot on. The N2 purge melts the immediate crystalline blockage on the filter, allowing the compressor to breathe again. But that thick sludge remains a localized, stubborn problem in the drain lines.
So the temporary fix gets the compressor running, but it doesn't solve the contamination.
Right.
To completely clear the arteries of the system and remove that heavy hydrocarbon contamination permanently, the crew has to execute hot gassing.
And that is a whole different beast.
Yeah, looking at the operational steps in the sources, hot gassing sounds less like pressing a simple defrost button and more like running boiling water down a grease-filled sink while simultaneously diffusing a bomb.
That is a very, very accurate description. It is a massive, non-routine thermodynamic deep clean.
It requires a formal risk assessment, right? And a JH.
Oh yeah. Because you are entirely circumventing the vessel's standard operational safety protocols. The crew must manually override the automated safety systems. They're manipulating the PID control loops and manually managing the variable diffuser vanes.
So you are taking a system designed to operate at minus 160 degrees and deliberately blasting it with heat.
Exactly. The forcing vaporizer sends warm gas between positive 20 and positive 40 degrees Celsius backwards through the LD suction side.
But wait, because the LD compressors are completely offline to perform this backwards flush, they aren't pulling any natural boil-off gas from the cargo tanks.
Which means the primary mechanism for managing the physical pressure inside those massive LNG tanks is completely shut down.
The pressure inside the cargo tanks is steadily and continuously rising.
The clock is ticking the entire time.
The crew is watching the tank pressure climb while they force positive 40-degree gas backward through the system.
Right. And before the tank pressure hits the 230 millibar opening set point, the crew has to execute a controlled emergency warm venting.
They are venting pure methane directly to the atmosphere, just to buy time for the hot gas to melt the sludge.
And venting methane directly to the atmosphere requires extreme external coordination.
I can imagine.
The crew has to adjust the ship's heading to ensure a strong crosswind pushes the vented gas safely away from the hull.
Wow.
The ship's air conditioning must be manually switched to full recirculation mode so you don't accidentally pull highly flammable gas into the accommodation block. The deck must be entirely clear of all personnel, and the gas detection system must be continuously monitored by the bridge.
It is an incredibly high-stakes, high-stress operation.
It really is.
You are managing vessel heading, wind direction, internal pressure limits, and backwards thermodynamic flow, all just to undo the damage caused by invisible heavy molecules that the official terminal paperwork confidently stated didn't even exist.
But once the sensors finally read positive 20 to 40 degrees at the boil-off gas cooler and compressor inlets, the sludge is completely purged from the arteries of the ship.
So it does work.
Oh yeah. The crew can finally realign the valves, re-engage the automated PID loops, and restart the normal cooling cycle.
So for the OSG listeners out there on the water, your cargo engineer's instincts were flawlessly accurate.
100%.
The historical 2022 notes, the uniquely slow-draining NBO pots, and these sudden cool-down blockages all point to chemical concentration, not a mechanical failure.
Absolutely.
Alternating the heel tank is absolutely mandatory to prevent that compounding brine buildup from happening in the first place. Minimizing pre-cooling delays, the Joule Thompson freezes, and understanding the distinct operational uses of an N2 purge versus the extreme intervention of hot gassing reclaims your control over the diagnostic process.
You know, this entire scenario highlights a critical vulnerability regarding the future of DFTE operations.
What do you mean?
We established that hot gassing, the only permanent fix to clear this heavy hydrocarbon sludge, relies on a controlled emergency warm venting of pure methane into the atmosphere before that 230 millibar set point is breached.
Right, and the maritime industry is currently moving aggressively towards zero methane slip regulations.
Exactly. Environmental rules regarding greenhouse gas emissions from commercial vessels are tightening every single year.
So if upcoming environmental regulations make it illegal or prohibitively penalized to vent pure methane during a ballast voyage,
how will crews physically perform this mandatory thermodynamic deep clean?
oh wow.
If an official legally binding document, like a certificate of quality, can confidently report zero heavy hydrocarbons due to a shoreside sampling blind spot while your ship's pipes are physically choking on solid pentane ice, what other official shoreside data points on the vessel should you be looking at with a much more skeptical eye?
That is a massive operational hurdle coming down the pipeline. You might solve the phantom problem in your pipework today by rotating your heel tanks, only to have environmental regulations take away your only permanent emergency fix tomorrow.
Yeah, you could find yourself with completely frozen compressors and absolutely no legal way to vent the pressure required to thaw them out.
That is definitely something to think about. Stay safe out there on the water, trust your hard-earned instincts when the gauges don't make sense, and for the love of the compressors, keep alternating that heel tank. We'll catch you on the next deep dive.